Did they hear me? We have a special seminar today. Dr. Sheng Wu is here to give us a talk. She was here for another meeting. So Sheng did her PhD in Canada, University of Victoria.
Yes. And
then she moved to Hopkins, I think with Andrew Wolf, to work on the hypothalamic control of reproduction. She stayed there as a junior faculty for a few years, and then she was recruited at Temple University at the Lewis Katz School of Medicine, where she's now an associate professor in the Center for Metabolic Disease Research. And Sheng has worked a lot and published a lot on, like I said, the central control of reproduction, GnRH neuron function. But she has established her lab on the effect of androgens in hypothalamic neuron, and especially in female, the negative effect of androgen excess. Using mice as a model of PCOS, she has actually developed her own model of DHT excess. And I guess she's going to speak today about this, the effect of androgen in reproduction and metabolism. Sheng, it's a pleasure to have you here.
Thank you. Thank you, Frank, giving me this opportunity to share my work with everybody. And it's really great pleasure to visit the Tulane University again. So as you may know, I worked with Frank for a while when we have some kind of a common sense to study the hyperandrogenemia. Sorry, it's okay. I think. So this is okay. That's good. Yeah, thank you, sir. So I still remember when I was a postdoc, and I found Frank's work is really fascinating, and we have so much common in studying the testosterone. So at the small phase, I preached him and asked, do you want to discuss some work with me? And in an endocrinology meeting, and he looked at me and said, sure, then that's how we work together. And I deeply appreciate his kindness and supportive to my research. So today I want to talk about what we studied in my lab. It's sexual dimorphic glucose homeostasis and energy expenditure associated with elevated androgens. Okay, so how do I go to next? Okay, so the objectives today is review of hyperandrogenemia women's health and discuss our studies exploring how exogenous hyperandrogenemia causes metabolic dysfunction. We have two models. One is we knock out the androgen receptor in liver, and another one we knock out the androgen receptor in the central nervous system. And then at the end, I want to talk about we just developed a new model is explore sexual dimorphic response of metabolic function to endogenous overproduced testosterone. We studied the offspring. So as we all know or may know, the elevated androgen is a key clinical feature in many women, including women with polycystic ovary syndrome, classic and non-classic congenital adrenal hyperplasia, exogenous testosterone treatment in female to male transgenders, which is a very hot topic now. And exogenous androgen use, like bodybuilders, they want to give the testosterone boost their muscle. And of course, the environmental toxicity. All these women, they suffer infertility and or metabolic dysfunction. So the PCOS affect up to 20% of women during reproductive age. However, this number is significantly reduced because only 50% of women with PCOS are diagnosed, and around 50 to 70% of women with PCOS have hirsutism. They have hair on the face or acne, and of course, in other body part of the body have a lot of hair. And those women suffered infertility, which is PCOS is the leading cause of female infertility. By itself, the annual health care costs over 4 billion. And those women not only have an infertility problem, around 50% of them are obese or overweight, and 50 to 70% of hyperandrogenemia or PCOS women have insulin resistance. With those ones, after these women reach the 40 years old, 12% of them will develop type 2 diabetes. So patients with PCOS really suffer a lot. They suffer both sides, infertility and metabolic dysfunction. These women very difficult to get pregnant. And even they get pregnant through multiple techniques or in vitro fertilization, they will face multiple problems: high blood pressure during pregnancy, miscarriage, gestational diabetes, premature delivery, or stillbirth. And finally, they have babies. What happened to their offspring? So they have a high risk of diabetes, obesity, and PCOS. Except those phenotype or problem, women with PCOS also have a higher risk of heart attack, increase lipid abnormalities, increase the prevalence of endometrial cancer, and higher rate of NAFLD. So our lab also study NAFLD now, but because of timing, I will not have time to talk about it. And they are more likely to develop anxiety and depression. So it's really hard to women with this problem. And the pathology of PCOS is still not clear. Even they diagnosed it in 1935. So according to the literature, we think elevated androgen is a key feature of the PCOS, and they cause the pancreas, liver, adipose tissue, make a metabolic dysfunction. However, recently we also find that in the lean PCOS, they may also target to the central nervous system to cause the metabolic function. Of course, the infertility part is a reproductive axis. It's a hypothalamus, pituitary, and ovary. Today, I will not talk about the infertility, but the major focus on the metabolic function. So the object two, where I will discuss our studies exploring how exogenous hyperandrogenemia through androgen receptor causes metabolic dysfunction. So the limited in the current field, as we may realize, is obese. So elevated androgen causes the metabolic and reproductive dysfunction. Obese also causes metabolic and reproductive dysfunction. When both conditions exist, if we want to study their mechanism, it's hard. Which is more important? So this is the important thing to make a new model. So to limit the obesity. So what we did is we gave a DHT pilot, which into the 8 weeks old mice. Then we look at their metabolic function and the hormone levels, reproductive function. Then at the end of 3 months of post the insertion of DHT, we harvest the tissues and look at what's the mechanism. So what we found, our published, we gave the DHT 4 millimeter length. Then we found twofold change of the DHT level compared to untreated, both by ELISA and mass spec. So with this dose, which we found that the body mass similar between control and DHT, and the body composition about the fat mass and the lean mass also similar. So whatever we see, the phenotype is not because of obesity, it's pure by the androgen. So we use the two models. The first model, we knock out the androgen receptor in the hepatic cells. Then we examine their metabolic function and look at their mechanism of molecular tissues. Then the second model is we knock out androgen receptor in the brains by the synapsin cleave. Then we look at what happened. So why we choose the liver? Because the liver may be the target by elevated androgen. When we look at the mice with DHT, the liver is insulin resistance. Adipose tissue also is insulin resistance. However, the muscle even have a better insulin sensitivity, which is makes sense because why all the people want to isolate, some of them want to give the testosterone or drugs because they boost the muscles. So then we look at the liver, we found another thing is because we gave the DHT, they have an impaired glucose, impaired pyruvate tolerance test. And the impaired pyruvate tolerance test tell us something happened in liver. They may increase the glucose production. Further, we look at the literature. Finally, we found one paper long time ago. People look at the liver. What they look at is a clinical study. They give the women with PCOS the same insulin, then compare the lean PCOS with the normal women. They found out the glucose production increased, and compare the obese PCOS with the obese non-PCOS women. They found even further glucose production at the same level of the insulin. So this further tell us liver is something happened. Then we look at it, we examine it with this model. We found the glucose tolerance, impaired glucose tolerance was restored by knockout androgen receptor with DHT. Here is the area under the curve. Then we look at the pyruvate tolerance test, the same thing. Control DHT compared to the liver AR knockout DHT is restored the glucose pyruvate tolerance test sensitivity. And also we conduct insulin tolerance test. Again, the insulin area under curve of the glucose also restored. So we know the liver is really a key tissue which was targeted by the androgen. Again, I want you understand this is a lean model. It's different from your group published with the obese model, which is published in the JCI, very solid conditions and with a lot of data. So we summarized when we gave the DHT or women with elevated androgen, they may have they may target the PI3 kinase, then they cannot phosphorate the AKT, therefore block the insulin cycling pathway. Further, the DHT also can bind to the androgen receptor as a transcription nuclease, transcription factor. Then they increase the PEP-CK and glucose 6-phosphatase. Together, inhibit the glucose uptake or increase the glucose uptake or increase glucose production, which target to the pancreas, increase insulin secretion, then eventually have a liver insulin resistance. This under the lean condition. Then another one, we want to study the central nervous system. So it's just happened because in our lab, we have this synapsin knockout. So I decided to look at. Another thing trigger us to study is because in your group published a very beautiful result, which said that the target to the androgen receptor targeted to the beta pancreas beta cells, which eventually make the beta cell failure with a high-fat diet. And all knockout androgen receptor in the brain target to the insulin liver insulin called insulin liver resistance, then develop diabetes. So we want to know without Western diet, what happened in the brain. So we used this model. So it's a long story short, we studied a lot, but we do not find very dramatic effect until when we gave DHT for 4 months. At that moment, the mice already 6.5 months old. So what we see is the glucose tolerance really improved by the knockout DHT compared to the control DHT. And compared to pyruvate tolerance test, because the knockout has a slightly higher, there are no difference, but the control DHT do increase the glucose. But there are no difference in the insulin sensitivity. So this tells us in the brain something happened, may improve glucose uptake or reduce glucose production in the liver. So then we go further, we want to see the energy expenditure or respiratory exchange rate. We found there are no difference between light phase, dark phase, and total RER between the control DHT, knockout, and knockout DHT. Further, we find out something happened in the energy expenditure. What we see is the DHT increased the energy expenditure. However, in the knockout, there are no difference. At dark phase, again, DHT increased the heat, but not in the knockout DHT. So the total heat produced by DHT significantly increased compared to control vehicle, and no change in the knockout with DHT. Then we, sorry.
This energy expenditure.
Oh yes, here. So in the very beginning, the body weight not changed.
Because in these females, obviously, you infuse DHT, they're gonna have increased lean mass, they're gonna have increased muscle mass.
Yes.
So that leads in itself to an increase in heat production. So that's why it needs to be controlled, corrected for body mass.
Yes.
So here it's
yeah, so I totally agree with you. So first, their body weight same as in the beginning I said, and the heat production, as I said here, it's increased, but you see the scattered, and I think it's a good concern should look at each individual body weight to correct it, maybe more accurate. And second, this heat production, it's not acute. It's treated with DHT 4 months. It's chronic. So maybe it's different. This may be the reason difference, but the mechanism why it's increased heat production, we do not know. And the food intake, we see during the light phase, they increase the food intake when we treated the DHT, but no difference or just slightly increased in the knockout DHT. So the total food intake is significantly increased in DHT. This one, I think it's difficult to see, it's very light. We need more data to prove if it's really restored by knockout the central nervous system.
Excuse me, let me continue what I was saying. So you show the body weight is unchanged, but they have increased food intake, increased heat production, which could be due to an increase in muscle mass, because it's a masculinization of body composition. So you could have an increase in muscle mass and bone mass, but a decrease in fat mass. and no change in body weight, you know.
Mhm.
And therefore, your increase in heat production and food intake is simply due to the increase in muscle mass. It's a masculinization of metabolism. It's not in rodents.
Mhm.
They have more muscle mass, they have more bone mass, the males, and that drives more food intake.
有面
So
也
did
没
you
有。
measure body composition?
Yes, yes. In the very beginning, the slides, we measure the lean mass and the fat mass, and there are no change. However, as you said, the bone density will also play a role, which I'm not familiar. But that's very good comments because I'm still puzzling why they increase the heat production and increase the food intake. So another thing we do just recently we got, just before I came here, one of the postdocs got some data about why they may, the mechanism why they have improved the glucose tolerance. One of the reasons is as people already published in male, when they knock out the androgen receptor in the central nervous system, the male will develop obesity, and they are increase the neurofactor kappa beta phosphorylation. So what we see is the IKK alpha is reduced in the control DHT, and the increased neurofactor beta increased in the control DHT. So this may, since the data number is not enough, so far only 3 control, it may through this pathway just knock out just the DHT inhibit, enhance the neural kappa beta, enhance the inflammation. So that's way people published in the Mayo, Dr. Chang's group. They say if they knock out the central nervous androgen receptor, then they will increase the neural kappa activation and inhibit the insulin sensitivity and the inflammation and reduce glucose uptake. So in the female, in our model, we think we knock out the androgen receptor, they reduced inflammation and enhance the insulin sensitivity, therefore increase glucose uptake. However, as Frank suggested, we do not know why they increase the heat production and increase food intake. Something can be considering POMC or agouti-related protein neurons, which is related to food intake and energy expenditure. And of course, the easiest way is we should carefully examine the lean mass. If they have more muscle, as Frank suggested, it may have the cause the increase the body, increase the heat production and food intake. Then the role of androgen cycling, as we said, in Frank's lab, they say it's the pancreas target to the pancreas with the Western diet, which is pancreas beta cells failure and eventually cause the type 2 diabetes. And in our lean model, we think maybe target to the liver and also the adipose tissue and the hypothalamus cause the metabolic dysfunction. So the last object I want to talk about the sexual dimorphic response of metabolic function to endogenous overproduced testosterone. So why we want to make an endogenous androgen model? Because the PCOS itself is endogenous high testosterone. All the exogenous cannot really mimic. It's so then we think maybe it's respond differently if we produce the endogenous testosterone. And in mice, adrenal do not produce androgens, only the ovary. So therefore we make a model, it's called inducible endogenous elevated androgen model. What we did is we created a mice with the RTTA in the RODA 26, and we have a crate CYP17 promoter clay, which supposed to express mainly in the thicker cells of ovary. And then we have another model is a tight operator by CRISPR inserted in the CYP17 gene. So we mated these three together. We created a mice with tight operator, which when we treated doxycycline, then they will confirmation of the RTTA attached to the tight operator, then increase the CYP17 expression, eventually make the protein, which is 1720 lyase or 20 hydroxylase. So what we found is we gave those mice doxycycline 625 milligram per kilogram. We found that there are 4.4-fold increase of testosterone. And in male, we found that around a 10-fold increase. With those testosterone level, we do not see the estradiol change, which in general, in the major population, the PCOS women, they have a similar estradiol, except the obese one. So unfortunately, we find out something which surprised us. First, we found the CYP17 expression in liver, dramatically expressed, not in muscle, and also in gonadal fat, pituitary, and hypothalamus, and of course in the ovary. So the ovary also, we check the protein level, they also increase. So then, whatever the phenotype we see in both male and female, it may cause from the liver or gonadal fat or pituitary hypothalamus. So which is unfortunately. So what we see is when we give the doxycycline, when they reach the 2 months old, in general, their body weight is similar. And the male also similar with doxycycline. And then we do look at the, before study the offspring, we do look at the male and female, and they have opposite result. So I do not think I have time to talk, but one thing is surprised us, the female actually do not have metabolic dysfunction. They kind of have improved. So we do not know why. And the male has a metabolic dysfunction. So then we think, okay, since there are so many things happened in the mice, how about we study the offspring, which we do not care if there are other parts expressed. The offspring is just pure female mice has increased testosterone. So we gave the mice doxycycline. After 30 days, we mate with male. At this moment, they have a high testosterone already, around 4-fold. Then we check if they could give any pups. They do have very few pups because the PCOS women hard to get pregnant, and they have very little pups and litters. So then we study the offspring metabolic function. So what we see is they have a timeline. So the longer, the older the mice, the metabolic dysfunction more severe. What we see is this male, you can see the offspring, female mom, which has a PCOS, their offspring has impaired glucose tolerance test here. And the pyruvate tolerance test at 140 days also significantly increased. And not happened in the ITT, insulin sensitive tolerance test. This is the male. So what happened to the offspring of the female? So far, we do not see much data, but we also look at the RER again in the triple mutant offspring. In the mom triple mutant, the mom is PCOS, their offspring has reduced RER, which tell us they consume more fat instead of carbohydrate. And the heat production also increased. So again, we did not check their body mass. It may have increased the muscle, lean muscle. And the activity is similar. And the food consumption is similar. And they are lower RER, as I said, just means they have increased and the increased heat production in the offspring. So they may just use the substrate differently. So the summary of this male mice, they have decreased the glucose tolerance and then worsened with age, which I did not show. At 1 month and 2 months and 3 months, they became worse and worse. And they have decreased pyruvate tolerance with age, suggestive of the activation of gluconeogenesis in the liver. And the RER also changed and the heat production also reduced. So all this tell us something happened. So we also have female data. So when I just summarize it, compare the female offspring from triple mutant mom with the male offspring from triple mutant mom. What we see is the body weight when they born from female mom, the offspring is reduced in the beginning and the male is slightly increased. The GTT female is similar and the GTT is impaired in male. Pyruvate is improved in the offspring and increased in the male offspring. RER, no change in female offspring, reduced in the male offspring. The heat reduced in the female offspring, but increased in the male. So what happened to this? We do not know. We haven't got a chance. So I really appreciate if you could give me some suggestions since we have a nice sexual dimorphic response, but we do not know the reason. In general, I would like to summarize elevated androgen, either endogenous or exogenous, they will definitely cause the infertility, which I did not show here, but it is. And elevated androgen may target to the pancreas, liver, adipose tissue to cause the metabolic dysfunction. And finally, I would thank the lab member, the postdoc Serene, Joseph, Weber, Huber. This tool gave all the contributions, the major data, and also, of course, our collaborators, Rex Ahima and Frank and Wen Hui in our university and NIH support. Thank you.
I'm here.
Yes.
So if you're in the audience and you want to ask a question, be sure to use the microphone so the people on Zoom can hear. Hold on. And then I'll also open up here.
Sheng,
Yes.
do you know this was very interesting. Do you know when CYP19 is expressed in your mice, in your
Yes.
pregnant female?
Yes.
What stage?
So they suppose during development, they supposed to have the CYP17 expressed.
Yeah, but during development, when? In first week, second week, or third week?
So we did not check so earlier. The earliest we check is 3 weeks. But according to the literature, the CYP17 protein supposed during embryos, the ovary already start to express.
Okay, I have a question. So in PCOS mothers, they are, in humans, they are sons and daughters. Do they have difference in their metabolic response?
Yes.
Like what you saw in your mouse model?
Yes. So in female, the women, they are the daughter from PCOS women. In general, they have a high risk of develop type 2 diabetes and obesity and PCOS also. In male, the the sun, so far in the literature, not too much information. So we do not know. That's we are look at our male model, but they do say the sun may also have metabolic dysfunction in some publication, but not a lot. They do say they have metabolic dysfunction.
So I had a question. I didn't really understand the transgenic model. I was going to ask you to go back to
The last one.
the last one,
Yes. Last.
this one.
Here. Yes.
yeah.
Yes.
But like, what exactly are you, hold on, I can pull it up here so other people can see. Like, what exactly, how are you making them have endogenous androgen? You're blocking us, you're overexpressing an enzyme?
Yes. So could you please go
Oh.
next slide? 25, slide 25. Okay, yes. So first we got a mice from Jackson Laboratory. They have a RTTA expression. And then we have this mice in our in the animal facility, which is a clay. This clay is driven by CYP17 promoter. So suppose only expressed or mainly expressed in the ovary thicker cells. And then this one is we made with our collaborator. He inserted a tight operator into the CYP17 gene. So when we mate this one with this one, they will take off the stop codon, then RTTA will be expressed. So once RTTA expressed, you must have doxycycline to make the RTTA have a conformation. They change the structure, then they can bind to the tight operator. So once the tight operator bind by the RTTA, they will driven the CYP17 mRNA expression, then eventually make the protein.
So
Yes.
you're overexpressing CYP17 in
Ovary.
what you found in
thicker.
other cells too. And where is CYP17 on this?
So
on this chart?
So this one is actually the ovary, how they express. So you see why the ovary can produce testosterone, because they express this enzyme in this one, can convert the progesterone to androstenedione, then testosterone.
Yeah,
So
but won't it just get aromatized to estrogen? Like how you're not really stopping the pathway from
Yes.
moving all the way forward.
that's where, I'm puzzling too. In women with PCOS, they supposed to have higher estradiol, but in general, if they did a mass data analysis, they find that actually the estradiol is not higher. In the
And
PCOS.
in your animals, you had what?
Not higher either.
Not higher, but the testosterone
It's-
was higher.
Yes, testosterone was higher. So for some reason, maybe the CYP19 is a limited enzyme,
Mhm,
which
mhm,
not changed. So
mhm.
then they do not increase estradiol. Yeah.
Estradiol may not be elevated, but circulating estradiol is a very poor marker of estradiol activity, especially women. So the bottom line, the point I'm making is that you can have low estradiol in serum,
Mhm.
which can have significant aromatization of tissue and production of local too. So unfortunately, the methods we have right now are totally archaic to measure cellular steroid output. The real method would be to measure by mass spectrometry the concentration of each and any steroids you want inside each tissue you want, because the serum tells you nothing.
Okay, yes, yes.
It's like a Jurassic plot of a measurement of hormone action. Steroids, we measure absolutely nothing with hormone action. Of course, when it's high, it's high. When it's low, you don't know what's going on in the tissue.
Yes, the tissue specific. I totally agree with you, Frank. So one thing is for sure, because the estradiol, each tissue has their enzyme, they may convert it in the tissue specific way. So we haven't really look at the ovary follicular, fluid in the ovary. maybe they have very high estradiol. Then in the circulation, while they not high, maybe they just metabolize immediately. I have no idea. But one thing, as Frank pointed out, actually the why liver is so important because testosterone can be converted to DHT in liver. So maybe that's another reason why liver plays an important role in the hyperandrogenemia cause the metabolic dysfunction. Yeah.
But your model is interesting, right? Testosterone is just a form. Testosterone is a weak hormone.
Yes.
It's nothing. Testosterone. It's a poor hormone. So you have a lot of testosterone circulating in cold tissue. And there it's transformed in T2 and DHT. So, your high level of testosterone is telling you that it's likely to be converted in both DHT and estrogen, where aromatase and reproductive are expressed. The brain, the muscle, the liver, wherever.
Yeah.
Pancreatic glands.
Yeah, so that's it's hard because our phenotype are not matched with the women with PCOS for the female part. So it's must something happen in some tissue which overexpress the CYP17. So we do not know. Maybe it's not in the muscle. We do not see difference, but the adipose tissue increase the CYP17 play certain role. We do not know.
Your model is actually very interesting. You should use it to decipher where aromatase and reproductive are active by measuring the conversion in those tissues.
So sorry, I didn't measure what.
You have a model where you have high testosterone produced by the ovarian with CYP17. But now you can use that model to measure where testosterone is converted.
Yes.
In vivo.
Yes, yes, thank you.
I had also another question about negative feedback, like thinking about the HPG axis. So when you give DHT to the female mice, does that have negative feedback on, LH and FSH? And then did the androgen receptor knockout, especially like the brain one, did that influence the feedback?
Okay, so the central nervous system, when we knock out, nothing about the reproduction. It's identical. So
the females have a normal vaginal smears.
So the knockout without DHT, the same as control without DHT. The knockout with DHT, the same as the wild type with DHT. So in general, the central nervous system totally surprises us. It's no difference in reproductive function. And
with the normal female, just wild type females with DHT, there is an effect on reproductive function?
Yes, so when you give DHT, they shut down the reproductive function in wild type. When you give DHT to the knockout, they also shut down the reproductive function.
So you see that in vaginal smears, or do you also look at like the uterine weight, or how else?
So we weight them with male.
Oh, you look at
We
actual
do not
pregnancy.
see when you give DHT in general, no offspring.
Mhm.
Yes, and of course they will not have cyclicity. Yeah.
All right. Any other questions? All right. Thank you, everyone.
Okay. Thank you.